All right, trust you did well on your quiz last lesson over the chapter 19. Students in here did fairly well also. We're going to transition now from reflection of light into talking about the refraction of light. Let's take a look at your homework first, though. You answered questions 1 through 6 on page 307. And question number 1 says, what is optical density? And Audrey, what did you have for number 1?
Optical density is a material's resistance to the transmission of light waves.
Very good textbook definition. Number 2, what medium has the lowest optical density and what has the highest? Michael?
Vacuums have the lowest optical density and diamonds have the highest.
Good. Now, if you put air for lowest, you're like, well, vacuum's not a medium. Okay, I would actually give that to you. So you could say air for what actual medium, but vacuum is the lowest, of course, because there's nothing there at all. Diamond is the highest. Number 3, define refractive index, and then what equation relates the refractive index to the speeds of light in a vacuum and in some other medium? Audrey, what did you have for 3?
Refractive index relates the speed of light in a vacuum to the speed of light in that particular medium, and the equation is N sub m equals C over V sub n.
Good. The definition really is the equation there, which is why as she's reading her definition, it sounds an awful lot like the question. It's one and the same. Number 4, what happens to the speed of light when it passes A from a vacuum into glass and B from water into air? What happens to the speed of light? Kendall?
The speed of light when it goes from a vacuum into glass is that glass is much denser, therefore it slows down.
Good.
And then from water to air, because there are plenty of water molecules in that of air, it travels a little slower.
Through the water, so when it goes from the water into the air, it can speed up. There we go. It's going to slow down going from vacuum into glass, but light is going to speed up going from water into air. Number 5, how are light rays refracted when they pass from air to glass and from air to water? Very similar type of question. How are they refracted, though? Michael?
When passing from air to glass, light rays refract toward the normal, and they also refract toward the normal when passing from air to water.
Good. In both cases, air to glass and air to water, it's going to slow the light down, and based on what we talked about in chapter 16, that means they're going to have to refract toward the normal. Number 6, we're actually going to get to this probably more tomorrow. We've got a little bit of a shorter lesson today with Pizza Day coming up. But what is Snell's law in its general form, and identify each variable? Kendall?
Snell's law is the incident angle of light and the refracted angle of light are equal.
Oh, no. They are not equal. If they were, there would be no refraction, right? If those two angles are equal, no refraction has actually happened. Now, you might have found it to say that, but that would be saying if they have the same optical densities, then that would be true. Michael, what did you have for Snell's law in its general form?
N1 times sine theta sub I equals N2 times sine theta sub R.
Very good.
N is the speed of light, theta sub I is the first medium, and theta sub R is the second medium. I can really tell.
Okay. Gotcha. Okay, yes. So the book presents it, if you look at the key equations up there, the book presents the Snell's law in its slightly different form. The way you gave it is the way I teach it. I'm like, is that in the book? It is in the book still. It's just not their final equation. So yeah, the way you said it is actually the way I want you to know it, but every year I say it's slightly different than the way the book ends up presenting it. But very good. All right, just a little thrown off. I'm like, did he already? I didn't record this video yet. That's weird. All right. Anyway, very good. And the n's in both cases you said were what?
The speed of light.
What does n represent, anyone from the reading? The refractive indices, which is based on the speed of light, but the refractive indices and the theta I, theta r are the
mediums.
Well, theta in general is used to represent an angle, so theta I would be the
angle of light in the first medium.
Or angle of incidence, right? Angle of light in the first medium. Then theta sub r would be angle of
reflectance.
Well, in the last chapter it was reflection. In this chapter it's refraction, if I can get the words out. There we go. All right. Again, we're going to talk about that more tomorrow. Next section in your notes, as we begin talking about refraction, you'll remember back in chapter 16 when we first talked about refraction, we said refraction takes place when a wave changes media and is forced to either slow down or is forced to or allowed to speed up. Does that make sense? So then, with this talking of refraction of light, we need to be able to talk about what would cause light to slow down. Well, obviously, if light comes to this desktop here, this countertop, the light is going to either be absorbed by the counter or it's going to reflect off the counter, right? Light is not going to go through the counter because this counter class is... There's a term I taught in chapter 18. Light can't go through.
Obscure.
Opaque, you were close. Opaque, very good. Light, this countertop's opaque. So opaque surfaces don't slow down light, right? We understand that. They stop light. We're going to be looking at transparent objects because light can go through those. That window, light can go through that. Argo's water tank, light can go through the water tank, right? We can see the blinds on the other side. We can see Argo lying on the bottom of the tank. There's a shrimp in there, by the way, a little ghost shrimp. Yeah. Anyway, he's supposed to help keep things clean in there. He may or may not also become a lunch for Argo later. We don't know. Just depends on how hungry Argo gets. Anyway, keep him fed and the shrimp lives longer. But light can go through transparent media, but different media cause light to travel at different speeds based on what's called optical density, if you write that term in your notes. Optical density. I'm going to give you the textbook definition first, and then I'm going to give you my definition. I just realized she has bromine sodium chloride up here. Textbook definition: a transparent material's resistance, a transparent material's resistance, a transparent material's resistance to the transmission of light rays. Good technical definition. It's very accurate. It's a good way to phrase it. But I'm going to give you a little bit more, if I were explaining this to Chloe, type definition in a second. A transparent material's resistance to the transmission of light rays. Now, transmission, remember, we're talking about passing through, right? We say a transparent material transmits light, meaning light travels through it, much like you travel down the hallway. Well, if you were to travel down the hallway now, when we let out class a little early on rare occasions, you transmit, if you will, down the hallway very easily. And then the bell rings, and there's little people, peasants, scum of earth even, and they get in your way, and these people in your way slow you down. Your transmission through the hall is encumbered, so to speak, is resisted by the existence of these others who inhabit the hallway. Transparent materials obviously consist of atoms and molecules, right? And those atoms and molecules get in the way, if you will, of light just passing through. Nothingness would be like the empty hallway, so to speak. Nothingness, class, would be a vacuum, where light can travel at its own natural speed. Again, there's some discussion as to what that may actually be. Since the one-way speed of light, as we've said before, is impossible to actually calculate. But assuming it's that 3 e8 meter per second, light goes through a vacuum completely unencumbered. Air molecules are moving constantly where they pretty much get out of the way. The speed of light passing through air is almost the exact same. We say, by the way, that in a vacuum, if you get some numbers down here, we say that light travels at 3.00 e8 meters per second because we're rounding to the nearest hundredth. We're going to 3 sig figs. We could say it's 2.998 e8 if we wanted to do one more decimal. But let's face it, it's easier to say 3 e8, isn't it? Light passes through air at 2.997 e8 meters per second. I mean, that's very, very close. Let's see, E8 would be 100 millions of meters per second. So 100 millions, 10 millions, millions, 100,000. What is that, about 700 or 100,000 difference? About 100,000 meter per second difference between light traveling through vacuum and air. Very little difference. Air doesn't slow down light much at all. It doesn't resist the transmission of light rays. But other substances do. Water. There's a lot more molecules there. They don't move as freely. The molecules are more in the way as the light attempts to pass through. Water allows light to travel at about 2.25 e8 meters per second. It resists the transmission of light rays. Here's the plain English. We would say that optical density is the ability to slow down light. Does that make a little bit more sense? The ability to slow down light. If you want to write that off to the side margin. The ability to slow down light. Now, testing and quizzing, I believe I actually use the book's definition, but as we talk about optical density, if we think of it as ability to slow down light, that helps. Think about it. Glass is clear. Light goes through glass. Is glass going to have more compact molecules or less compact molecules than water? Well, it's a solid, right? So it's got to be more compact. There's got to be more stuff in the way. Still transparent, light still goes through, but there's more stuff in the way. This is a really full hallway. We're down to 2 E8 meters per second. And I'm going to go only one, I'm not going to go 3 sig figs on this one because there's different types of glass, okay? Different types of glass affecting differently. It's kind of an average number for glass. It's right around that 2 E8 meters per second. The most optically dense substance of all, as was asked in the homework class, is a diamond. We're going to talk later about why the diamond gets its sparkle this way, but diamond slows light down all the way down to about 1.24 E8 meters per second. About 1.24 E8 meters per second. That's less than half of what it would travel in air, for instance, right? That's less than half, not even half. It's really slowed down at this point, and that's what allows the diamond to get its sparkle. Diamond is the hardest substance, most dense. It's also the most optically dense substance known to man. Now, what happens then as light slows down in these other media? Or is light, maybe for instance, goes from one of these medium into air, light's going to change speed. We said that as any wave changes speed, it will change direction with respect to the normal, or it will refract. Refraction, next term we're going to write down. This is a repeat definition, if you will, but refraction is the change in direction as light changes speed. Refraction is the change in direction as light changes speed. Refraction, the change in direction as light changes speed. Now, we do understand this. There are things like prisms, for instance, that will cause light to disperse out into its colors, right? But for the most part, what's on one side of a piece of glass is the same as what's on the other side of the piece of glass, right? Largely, unless it's tinted glass, that greenish glass or whatever. But if there were a blue jay sitting out there in the tree, we would see its blue coloring, right? That means that the frequencies of light, as they travel through most media, the frequency of light does not change because frequency is color. But remember, wave speed, you don't have to write this down, wave speed equals wavelength times frequency. Both of these affect wave speed. If the frequency does not change and the speed does, what must change with it? Wavelength, the other thing, right? Since the frequency is constant, if the speed increases, wavelength increases. If speed decreases, wavelength decreases. And it's actually this change of wavelength that causes the refraction. The wavelength shift causes the bending, if you will, of the light ray. Now, what we need to remember, and again, this is review for us, but it's been a little while, if the light is able to speed up, if that speed increases, that wavelength increases, it's going to bend away from the normal. If the light speeds up as it goes from, for instance, glass into even water, or from diamond into glass, or most of these into air, right? If the light speeds up, it's going to bend away from the normal. If light slows down, that is that the light goes from air into one of these media. Maybe we shine a laser beam into Argo's tank. That could blind Argo. Let's not do that. But if we shine a laser beam into a tank of water or into a swimming pool or what have you, as the light hits it, it's going to slow down, causing that decrease in wavelength, which is going to cause the wave or the ray, as we're thinking of it in geometric optics, it's going to bend toward the normal. And all of this is review. We remember this from chapter 16, talking about refraction. Now understand this as well. As we think about, for instance, Argo's tank, we think about the window, we think about anything like this. If an object is opaque, it's non-transparent, light's either absorbed or reflected, no light goes through, right? But even with a transparent object, does all light necessarily transmit? No. right? You've been in one of those cases where, for instance, you look through a window and you can vaguely see your own reflection, and then you can see into the room as well, right? Especially if the room's dark or the glass is tinted. You see your reflection much better, don't you? Whereas if it's bright on the other side, for instance, if we all went to that little window there or that window, I might see a little bit of reflection of myself, but mostly I see what's coming through the other side because there's a lot of light passing through. But at a transparent boundary, some light can be reflected, some light can be transmitted through. We're going to see this when we play around with different transparent media later on, not today, unfortunately. But as we shine a laser beam, you'll notice there's a reflected laser beam, and then there's the laser beam passing through. Because at a transparent media, some light can be reflected and some light can be transmitted through. Does that make sense? What makes the difference, this is what you need to know. If two transparent objects have the same optical densities, well, then light isn't going to change speeds at all, is it? Same optical densities, light will be fully transmitted. If two objects have the same optical densities, light will be fully transmitted. No light will reflect off of that boundary of the medium because it's the same optical density. There's nothing to change the speed. However, if you have differing optical densities, so same optical densities, fully transmitted. However, if you have two transparent objects with different optical densities, and this is usually what we'll encounter, even with, for instance, you ever been to an aquarium or something, right, where they got that thick glass that you're walking through or walking next to, they got pretty thick glass, and you got water. Well, you've got air, glass, water, three transparent media all right next to each other. All of them, light travels at different speeds. So what you're going to get in that instance is some light will reflect, some light will refract as it transmits. If objects have different optical densities, some light will reflect, some light will be transmitted but refracted. Just want to make sure we understood that. We're not going to get all the light going through the second medium if we have different optical densities at the boundary point. So we get two different speeds, right? Light's traveling at one speed, reaches a boundary, it's new substance, new medium, maybe, again, shining a laser beam down into a swimming pool or something. And I don't know what you're doing with it, maybe driving fish crazy or driving people crazy, whatever. Shining a laser beam down a swimming pool, because the light is going to change speeds, the light's going to refract, correct? It's going to change speeds in the new medium. Or if you somehow had a laser, you could operate underwater without, short-circuiting the laser. And you were shining a laser beam. Well, same thing's going to happen, just in reverse. The laser beam, as it exits the water, is going to bend, this time away from the normal as it speeds up. We have two different speeds then, and we can compare them. We can make a ratio with them. We call this ratio the refractive index. The refractive index, or the index of refraction. I prefer refractive index because I'm lazy, and it's one less word. Yeah, I am that lazy. Refractive index is defined as the ratio of speed of light, though we're going to compare everything to the constant, right? The standard. And the standard is a vacuum. So a refractive index then is the ratio of the speed of light in a vacuum, which again, it's not that different from the speed of light in air, I get it. But the ratio of the speed of light in a vacuum to the speed of light in some other medium. The refractive index is the ratio of the speed of light in a vacuum to the speed of light in some medium. In equation form, we could say that n, that's what we're going to use for refractive index, sub m, meaning the refractive index of some medium. N sub m, refractive index of some specific medium, equals c, you remember we use c to represent speed of light in a vacuum, over v sub m. V being the speed of light in, again, that same medium. This is the first equation that you'll need for this chapter. Refractive index. We'll compare the different speeds, right? We have all these different speeds roughly at which light travels through these specific media. There are lots of other media out there as well that are clear, transparent. If we take the speed of light in a vacuum over the speed of light in some other medium, it gives us its refractive index. Now, which of these is going to be greater? The speed in the vacuum or the speed in the medium? Vacuum for sure. So we're guaranteed an improper fraction, so to speak, with the ratio, right? So we're guaranteed a value over 1. So all refractive indices will be over 1. Does that make sense? In fact, if you look on page 294, page 294, you see a listing of different refractive indices there. I do want to point out, first of all, vacuum. A vacuum has a refractive index of exactly 1. Right? Obviously, you compare the speed of light in a vacuum to the speed of light in, say, a vacuum. Well, they're going to be equal, of course. It's the same thing. So you're going to get exactly 1. Notice air, 1.0003. Barely bigger than 1, because light barely slows down through air. But you get into some of these other things, right? You got carbon disulfide, whatever that is, 1.63 crown glass. That's a specific type of glass. Differentiated, for instance, from flint glass, borosilicate glass. There's all different types of glass. Diamond, notice is the highest number on there, 2.42. It's got the biggest refractive index because there's the biggest difference in the speed of light there. Water, you see 1.33. Quartz, zircon. You ever heard of zircon, ladies? Cubic zirconia, perhaps? You've heard of that before. Fake diamonds, if you will. Right? It looks like a diamond. It sparkles sort of like a diamond. If it's cut really well, it sparkles really well. I'm cheap, okay? So my wife she does have a diamond in her engagement ring, for the record. You get engaged one day. Don't try to cheat and get cubic zirconia for the engagement ring. But I recently bought her a nice necklace, and it looks beautiful. It's got this gigantic diamond. It's not a diamond. She knew it wasn't, because she knew I couldn't afford something that big. It's cubic zirconia. It sparkles really nice, though it's cut really well. That's the next highest number on here, notice. Right? You got diamond at 2.42, zircon at rounded, again, these are approximated, 1.92. That's the next highest number. That's the next best refraction that you're going to get. So that's why cubic zirconia is used, and it's not uber cheap. It's not like, little crystals or whatever. But it's not nearly as expensive as a diamond. Okay, so cubic zirconia can still look nice. Just don't try to lie and say it's a diamond if it's not, because you're not going to get the points in the end. She's going to figure it out. But anyway, and it says imitation diamonds can be detected by their refractive index. Their refractive indices are not going to be that close. And so you can figure how the refraction is taking place. Questions on index of refraction, or refractive index. Notice the plural refractive indices. Okay. Questions on that? Look at the example problem right down there at the bottom of page 294. Read that for us, if you would, Michael.
For a certain frequency of light, a diamond has a refractive index of 2.42. What is the speed of light in diamond?
All right, so this particular light, this particular frequency, refractive index comes out to the 2.42. We see what's the speed of light. And so if we wanted to find the speed of light, that's the V sub m, isn't it? We already know the n sub m. In fact, you could Google lists of refractive indices. So we often don't need to find refractive index. We often are curious, okay, if this is the refractive index, how fast does light go through this substance? What would I do to solve for the V sub m in the equation class? Good, just alternate, right? Take the C, which we'll use 3.00 E8, over the n sub m. So if we take 3.00 E8, and we divide by that approximate refractive index of 2.42, we get what speed of light for the diamond?
1.239.
Yeah, big old number, so you put it in scientific notation, 1.239, approximately, as we said before, 1.24 E8 meters per second. Right? If we wanted conversely to find the refractive index, of course, if we knew the speed of light, we could divide. Turn over to page 307. Turn over to page 307 in your textbooks, and take a look at problem number 1. Read that problem for us, if you would, Audrey.
A certain kind of glass has an index of refraction of 1.52 for yellow light at 589 nanometers. What is its speed in this glass?
What is its speed, meaning light's speed in this glass? Notice they give you the refractive, they give you the nanometers. Do you remember what nanometers would be? E negative 9, but nanometers there is referring to wavelength. So that's the wavelength of the light. Oftentimes if you buy a laser, it'll tell you the nanometers of the wavelength of light that's coming out. So that's all it's giving us there. Does the wavelength necessarily matter here? No, even though it will change, the frequency will stay the same. There's nowhere really to plug in the wavelength, so we're just going to ignore that number. It's a little extra distraction here. It's just giving you what specific yellow light we have. It says the index of refraction is 1.52. It says for this type of glass, how fast does light go through? Very similar to what we just did at your seats. Solve. The n sub m, the index of refraction, for this particular type of glass is 1.52. So how fast does light go through? And Kendall?
2.58.
All right, so we know the refractive index is 1.52. We know that C is 3E8 for sake of time, and then we're solving for the V sub m. So we said we had to do what again? Alternate and divide. So we should have
1.973.
good. I think it's 3 sig figs here that we're looking at. Yeah, so 1.97 E8 meters per second. I said most types of glass are right around that 2 E8 meters per second. About 2/3 the speed of light is right around there. If we rounded to 2 sig figs, we would have had the 2.0. Did we get 1.97 E8 meters per second for the speed of light in that glass? Number 2 is an interesting problem. Read that one for us if you would, Michael.
The speed of yellow light at 589 nanometers is measured to be 1.92 E8 meters per second in a certain liquid. What is the index of refraction for this liquid?
So remember, we just calculated for this particular type of glass, light travels at 1.97 E8. There's a liquid that actually slows light down even more, all the way down to 1.92 E8. What would be the index of refraction? At your seats. We somehow measured the speed of light through this liquid. The question is, what is the index of refraction? Again, it's going to be a higher index of refraction than we had in the glass for the previous problem because it slows light down more. More slowing effect, higher index of refraction. And Audrey, what you got?
3.26 E5.
All right, so we're finding the index of refraction, the n sub m, right? We know C, that's the 3E8, and it says in this liquid, light travels at what speed?
1.92 E8.
1.92 E8, so we just need to divide these. By the way, I want you to notice speeds are going to be in meters per second, but what's going to happen with the meters per second, class? They cancel. And that's true in all ratios, right? Ratios, units cancel. So since refractive index is a ratio, it is unitless. You may want to jot that down. Audrey's redone the problem. Audrey, what is this refractive index for this particular liquid?
1.56.
Good, 1.56 if we were to round to the 3 sig figs. Let's flip back to page 294 and see if there's any liquids on here that are around 1.56. I mean, if carbon disulfide is a carbon, I can't imagine that's a liquid. Methylene iodide is probably a liquid. That's even higher refractive index. I don't know, maybe some thicker liquid like a thin oil or something, maybe. I don't know. What?
I said polystyrene, but that's a solid.
Yeah, that's also solid. So probably some kind of oil, like a vegetable oil or something like that, might have a refractive index up around the 1.56 mark maybe. But again, it'd be a thicker liquid, a more dense liquid. Now again, density related to water, less dense, but optical density, higher optical density liquid there. All right, questions on that? All right, I'm going to give you your homework, and then there's one more video we're going to watch. If you're watching on YouTube, the link is in the description of the video. For homework this evening, though, I need you to read over pages 294 to 299. I need you to read over pages 294 to 299. And on page 307, answer questions 7 through 11. Page 307, answer questions 7 through 11. All right, and we'll go and watch that video now.